Just make sure that these variables where we have stored our mean scores and are matching the variables that you have created here. Sure that you don't run into any errors. So let's visualize that now, and then we'll compare these results. So we have around 86 for F1 score, 92 for recall. Okay, so the accuracy, session, recall, and F1 score. The highest is the recall. The accuracy was around 84%. And then we have 82% for precision. Let's go back and remember our scores here. Here it shows that it's higher than the cross-validation. If you recall that we said that these classification or these metrics were made based on the two data set splits, 80% of training and then 20% of testing or test data sets. So it seems that it has a higher evaluation metrics compared to the cross-validation. But this is not the final decision that you can take here. So if your evaluation metrics, from the two data splits, the training and test data splits are higher than those came from the 5 folds in our case, okay? So the decision on which evaluation trust depends on several factors. It depends on the, understanding the two data split evaluation. So in our case that we have 80 to 20%. So the pros, let's talk about, pros and cons on each of these, two data split evaluation. So the pros is it's straightforward and computationally less expensive. It gives a quick estimate of the model performance on a specific data set split, okay? On the other hand, you have a con where the results can be sensitive to a specific data split. If the training or test set isn't, representative, the evaluation might not generalize well on another unseen data, okay? On the other hand, also let's understand the cross-validation. So the cross-validation involves splitting the data again into multiple subsets. In this case, we have 5 folds, training and testing the model in different combination of the folds. This helps to assess the model performance more in more robustness way, okay? The pros here, it gives more stable and generalized estimate of the model performance, as it tests the model on multiple data splits and it sees all of the data. So it's especially useful for small data sets, as each data point gets to be, on the test set. A disadvantage here or a con here is that the cross-validation, might be computationally expensive and take longer time to run, especially with larger data set or complex model. But here the question is why cross-validation might be a better choice for you. Cross-validation, as many times we say that its generalization ability. So cross-validation helps estimate how well the model generalizes to new and unseen data, since it tests the model on different portions of the data set. And the performance metrics obtained are more reliable and representative of how the model will perform in real-world scenario. Also, it has like less variability. Cross-validation reduces the risk of overfitting or underfitting to a specific training or testing split. Okay, a model performance might be different on single test set depending on the data distribution. So cross-validation mitigate this risk by averaging the results across multiple test sets. Okay. So it depends, as I mentioned here, on which one, how sensitive your data is, how big your data is, who's taking a decision here, whether you are very sensitive for errors. In our case, yes, we are very sensitive to these false positives and false negatives, since this is predicting a heart disease. So it might, be very critical to have very robust results and very robust model that can, predict unseen cases in the future. Experimentation. So, this is all part of the experimentation. If you recall that we have uh, when we were explaining why experimentation. So experimentation is the last step here, and it's very important step here. So as you know, in case if you haven't hit your evaluation metrics yet, you could ask yourself, for example, could you collect more data? Why this helps? So more data can help the model to learn better and make more accurate prediction. It is especially useful if you are facing issues with underfitting, when the model is too simple or the current data set is very small. Okay. A question here is how we can, collect more data. You can gather more data by using, public data sets, for example, or scraping the web, using, crowdsourcing or leveraging domain-specific sources. Also, there is a technique called data augmentation. It can, generate synthetic data, particularly for domains like image or text. This is in case if, your issue is with the data. But what else that we can, for example, try here? Can we, for example, try a better model like cat boost or xg boost? Maybe we haven't talked about that. Let's, have a summary on that. So why does it help, to try a better models or new models like, xg boost or cat boost? These are specifically designed for better performance on complex data set, in case if you're dealing with a very complex data set. So these models handle non-linear relationship with missing values, and it has like a better than simpler model like logistic regression or random forest classifier models that in our case that we are using. So it handles more complex, data set. The XGBoost and CatBoost models. An advantage of each of them, like the XGBoost, is highly optimized, work well on imbalanced data set, and handles a large data set effectively. Okay. And CatBoost, on the other hand, it handles like categorical variables natively without the need of pre-processing, and it's faster than many other models. But when to use both of them? So these models are particularly effective for structured data. Okay, in our case, also structured, and when you want, to squeeze out the best possible accuracy scores, maybe we can try that later, as we are trying to predict heart disease, which is very critical in our case. What else that we could ask ourselves that we haven't experimented? Like, could we improve the current models beyond what we have done so far? Part of that question and answer here is that we might look for future engineering. So maybe we can create new meaningful features of the or combining an existing ones that can significantly boost the model predictive power. So If you recall that when we were doing these feature engineering and we tried to understand the correlation here of these, so you might, correlate the maybe the age and sex, and then create a new column, call it age and sex is equal to, for example, you put a condition of the age if it's more than 65 and then sex is female. You might have a higher probability of a patient getting a heart disease. So, you can create a new column and you call it female and age, or, sensitive to, to heart disease. And then, you can put it yes or no, or 1 and 0. You know, there are many different ways that you can, come up with a good feature engineering. And that, include like adding also interaction chain between the features, or extracting new features, from existing ones. Like in our case, if you recall that one of the critical cases or critical correlated values with detecting the heart disease was the chest pain type. If you recall that it has around zero point zero 0.04 a correlation on predicting whether a heart disease patient might, so these were the values. Maybe you have, if you've noticed that maybe the two type or two, the second category or the first category has a higher chance of getting heart disease, you can maybe create a new column here saying that level of the chest pain. These all can bring you more accuracy to your model, focusing on a certain variables within your data set. Also, as we have done like hyperparameter tuning. While we have already used like the grid search CV and the randomized search CV, exploring larger hyperparameter search spaces or fine-tuning parameter further, can lead to small but really a significant improvement. Also, there are like ensemble methods that we already have used. The ensemble method, you can use them combining multiple models like the random forest and XGBoost into an ensemble method like bagging or boosting or stacking. This can improve the prediction accuracy and the robustness of your model. Also, as we have done already, the cross validation in our case, like using more sophisticated cross validation techniques like stratified k-fold or imbalanced dataset, or exploring different splitting strategies might improve the model performance. So this is all about this section that we have. We gone through all of these steps. From we evaluate our problem, we set our goals, we have seen the data, done some baseline evaluation, we have we explored the features or the correlation of the features, we have seen how important it is to the model. We have done some modeling using 3 main models. We tried to experiment and try the cross validation to see whether it has better accuracy. We tried to fine tune our model. So almost we have gone through all of these steps. To be more okay, so here we are done, and then the final model evaluation, point 9. Lastly, next we are gonna explain how we can save and might deploy the model. This is an optional thing for you in case if that you have hit your evaluation metrics, and you might have a place to deploy your model. But mainly we'll focus on how to save and load the model in the next session, and it's gonna be the last session.